Hey, what are you doing here?
I'm here to add a little perspective. First, let's get you closer in scale to me. Good.
Whoa, 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 come on!
Next, well, get away from me.
What exactly are you doing?
Well, there seems to be a little confusion about today's astronauts and those who went to the moon. I thought I'd offer a little perspective. So today, astronauts travel to the International Space Station. It sits in low Earth orbit, right about here. Today, astronauts have to travel about 250 miles from the Earth to get to the International Space Station.
Fascinating. Can we get to the moon part, please?
I'm getting there. Hold your green cheese. To get to the moon, however, astronauts had to travel about 240,000 miles away from the Earth. And they took a very specific path from the Earth to the moon, where they landed.
Ow! That's my eye!
Once there, they set up experiments, took lots of photo and video, and picked up some rocks to bring back. While 2 astronauts were on the moon, a third one was in the command module orbiting around the moon.
Like a little fly. Can we get these astronauts off of me? They're walking all over my face.
When the other 2 had finished on the surface, they launched into orbit and hooked up with the command module, which brought them all back to Earth.
Nice. Can we make me normal head size now?
I suppose.
Okay. So other than the moon being a really long way away, what have we learned since the Apollo moon program?
At least 30 minutes worth of stuff.
This is STEM in 30. Wait a minute. I don't have any hands to point at the camera.
It's probably for the best.
This is 7:30.
Hi, I'm Beth.
And I'm Marty, and check this out. This is a Saturn V F1 engine, the type of engine that took humans to the moon.
We are coming to you live today from the National Air and Space Museum. Now, we are going to be in our newest exhibit, A New Moon Rises, and these are images from the Lunar Reconnaissance Orbital Camera, or LROC for short. To get started, though, we'd like to welcome our online audience. We have a moon expert, Jenny Witten, who will be answering questions that you submit, and we might take some live on the show.
We also have Whittier Education Campus joining us today. They've got some great questions ready to ask our experts. Now, 40 years ago, we went to the moon, and those sites are still there because the wind and the rain don't exist on the moon. So those sites are still pristine.
Now, LROC has taken a lot of great images that we can see that shows us craters and valleys, and as Marty said, even the Apollo landing site. Now, we haven't been to the moon for 40 years, so why are we still interested in it? We'll be taking a look at that today during the program, but first, let's take a closer look at our closest natural satellite.
The regular daily and monthly rhythms of Earth's only natural satellite, the Moon, have guided timekeepers for thousands of years. The Moon's influence on Earth's rhythms, such as the ocean tides, has been charted by many cultures in many ages. The light areas of the Moon are known as the highlands. The dark features, called maria, are impact basins that were once filled with lava. These light and dark areas represent rocks of different compositions and ages. The craters themselves, which have been preserved for billions of years, provide an impact history for the Moon. Over these billions of years, the surface of the Moon has been ground into fragments ranging from huge boulders to powder. Today, the entire Moon is covered by gray powdery dust and rocky debris. Upon first seeing this landscape, astronaut Buzz Aldrin proclaimed, It was once thought that the arid, lifeless moon had not changed very much geologically for 1 billion years. Recent studies using the Lunar Reconnaissance Orbiter have shown that the moon is much more dynamic than we thought.
And now I'm joined by Dr. Tom Waters, who is a senior scientist here at the museum in the Center for Earth and Planetary Studies. Tom, thanks so much for being here.
Oh, my pleasure.
Now, you are on the Lunar Orbiter, the LRO mission. I'm sorry, I just lost it. And you also curated this exhibit. So do you want to tell us a little bit about why this program and this exhibit are important?
Sure. Now, the Lunar Reconnaissance Orbiter
That's what I was...
mission actually had two very important goals. Many of you probably don't know that it's in orbit right now, and it has been since 2009. So one of the goals was to prepare us to put humans back on the moon. Because, as we talked about, we haven't been to the moon, humans haven't been to the moon in 40 years. So one of the jobs that we had is to study a whole bunch of areas on the moon, actually 50 areas on the moon in great, great detail, to prepare us for that opportunity to go back to the moon. And we're doing that using these very special instruments on board the Lunar Reconnaissance Orbiter, which includes the cameras. And the cameras are really special because two of those cameras are actually telescopes. And they're taking really high resolution images of the lunar surface. Oh, and I'm sorry, the second part of it I want to finish was to do science. We wanted to use those very special cameras to study the moon in a way that hadn't been possible before.
And you've gotten these images back. Have you seen anything that surprised you about the
Oh,
moon?
absolutely. If I can show you some pictures. One of the things that really, really surprised us was features like this, these little blobs that turned out to be volcanic lava flows. Now, we thought the moon had been inactive for 1 billion years. In other words, the last lava flow that we thought happened on the moon was 1 billion years ago. When we saw these things, it was like, oh my gosh, these are really young. They have almost no craters on them. They're so young, in fact, they probably happened less than 100 million years ago, which means that the dinosaurs could have been looking up at the moon and seeing glowing red as these lavas were flowing out onto the surface. The other thing that we found in some of these images were these scarps, these fault scarps. They're actually formed when the crust of the moon is pushed together. And we knew that there were a couple of these. In fact, at the Apollo 17 landing site, the last landing site where Apollo astronauts visited, there was one of these fault scarps. But we didn't know how many they were until we got into orbit with the Lunar Reconnaissance Orbiter. Now we've found thousands of these faults all over the moon that are indicating that the moon is actually shrinking. But don't worry, it's not going anywhere. It's shrinking only by a little bit.
Now
but
I'm joined by
really
Dr. Alan
cool
Nadell.
is
Alan, thank you so much for being here.
It's not happening millions of years ago. It's happening now. The moon is actually slowly contracting as we sit in this room.
And so this is happening a lot, not as long ago as you thought. So the moon is still pretty active.
That's the thing. That's one of the big surprises is the moon is not this lifeless body. It's still geologically very active.
Now, as you said, we went to the moon, and one of the things we did while we were at the moon was collect moon rocks, but you couldn't just walk around and pick them up. You had to have special tools. And I got a chance to talk with Alan Nadell, and he showed me some of these special tools we used.
Now I'm joined by Dr. Alan Nadell. Alan, thank you so much for being here.
It's my pleasure.
Behind us, there's a whole bunch of stuff in this case. Do you want to tell us a little bit about what's in here?
Sure. One of the fascinating things about the lunar exploration plan, the human exploration plan in the 1960s and 70s, was how much preparation they did and how much planning they did for doing the essential aspects of the missions. One of which, of course, is to collect samples. Why go there, walk around if you didn't bring anything back? And so the astronauts had a whole bevy of tools. The first astronauts basically only had the tools that they could carry attached to their belts. By Apollo 14, they had a little wheelbarrow with a tool carrier where they could have a bunch of tools. And of course, 15, 16, and 17, they had a lunar rover, a car.
Now, I noticed that a lot of these tools have longer handles than we're used to here on Earth.
You'll notice, first of all, that there are two various lengths. The shorter ones were used, as I said, on the earlier missions when they had to carry them attached to their belts, or later on they got longer. There are a lot of advantages of having long. One, the suits are fairly stiff, and although they actually fell down a few times and were able to get up, basically they had to move around like that, and there wasn't a whole lot of stooping.
Sort of waddle.
Right, there wasn't a whole lot of stooping, and so they needed the extra extension. One of the things that's a little bit frustrating to us is we have no flown tools.
No, really?
No, why would they bring a tool back? They knew everything there was to know about a tool. Every ounce was important. And so to bring any of those back would be to sacrifice the ability to bring back another rock. There's one interesting tool here. It's called the contingency sampler. When Neil Armstrong stepped onto the moon, one of his first jobs, before he did anything else, was to use the contingency sampler to scoop up some dirt. Because if something went wrong and they said, abort, abort, climb back in, we have to go, they wanted to have at least one sample to bring back. And so the contingency sampler is one of my favorite objects. One of the challenges was to get the samples back to Earth not contaminated by particles from hair or skin or any of the other things that would have been naturally contaminating the atmosphere inside the spacecraft. And so Union Carbide Corporation developed these Apollo lunar surface return containers, or what we call rock boxes.
Rock box is easier.
And their design was to be triple sealed so that as the containers and rocks and soil were put inside, it could be closed very tightly and then to keep contamination. It didn't work perfectly, but it certainly enhanced the purity of the samples that the scientists could examine when they got back to Earth.
Well, thank you for explaining all these interesting things to us. I appreciate it.
Well, my pleasure. Thank you.
So Tom, are we ready for some questions?
Yes.
Let's start with an online question. What other instruments beside the camera are on board the LRO?
Oh, that's a great question. There's actually 7 different instruments on the spacecraft. I work with, again, the cameras, but one of the other instruments is designed to give us elevations. So there's a laser that actually fires pulses to the moon and then looks for them to bounce back, and that gives you a measurement of how high and low things are. There are other instruments that tell us things about the composition of the surface of the moon. So all those instruments together allow us to do some really, really great science.
Okay, and we have an audience question. What's your question?
Can a moon sustain life?
Can the moon sustain life?
Can the moon sustain life? It's a great question. The biggest problem the moon has in sustaining life is that it has no atmosphere. So it's literally, there's nothing there. So there's no air to breathe of any form or any kind. So if you're going to live on the moon, you pretty much have to build a place. You have to build a place that you can bring the oxygen that you need to breathe, and you have to kind of protect it. You have to put it somewhere where it's not going to get hit by very small or even larger meteors, because the moon has no protection the way the Earth does. The Earth's atmosphere protects us from a lot of small and even some fairly big objects, but the moon doesn't have that. So you want to be careful about how you build it, but yes, you'd have to build the place to live on the moon.
Well, thank you very much. Marty got a chance to go to his former school, South Valley Middle School in Liberty, Missouri, and he brought them a special treat.
I am here at South Valley Middle School in Liberty, Missouri, and I got to tell you, I'm really excited about this. This is my former school where I used to teach, and I actually graduated from Liberty High School a long, long time ago. Now, some of you guys were actually in my class. Raise your hand if you used to be in my class. Awesome. Well, today, we're going to be making impact craters just like on the moon. You guys are going to have marbles. You're going to hold them up above this simulated lunar surface that has flour below it and a thin layer of cocoa on the top. We're going to drop the marbles in to see what happens when a crater is formed on the moon. That's pretty cool, huh? You guys ready to do this? Yeah. Let's go. Oh, nice one. That was cool. Check that out. You've got the ejecta right over there. What do you think would happen if we dropped it from higher or lower?
Make a larger impact.
Okay, larger or smaller depending on how much speed it's got. Good. You want to do that one?
Yes, I would like
All right, let's go right in here. Oh, now wait a minute. Look at something here. Do you guys see the white there? Did you notice that that came out of the crater?
Yeah.
When that hits with enough force, it actually takes what's underneath and throws it out on top. And we can see that, and it's called ejecta. And what's cool about that is when the astronauts went to the moon, they were able to find ejecta from craters and pick that up. And that rock that they picked up that was considered ejecta was actually from inside the moon, not just the surface. So we could study the surface of the moon by picking up just any random rock, but if we picked one up that had come from inside a crater, we knew we had a rock from inside the moon. We're going to try something different now. I want you to drop another one. And this one I want you to drop right here. Can you do that? Yep. Okay, now we've got two craters. This one kind of got messed up, didn't it? So can we tell which one's newer?
the one that's less deformed.
Exactly. So when we look at the moon now, we can see that craters that are fully formed are probably newer than ones that maybe have an overlap in them. So you can actually tell ages of craters on the moon by how they overlap other craters. You guys did a great job making craters on the surface of the moon, but I thought it might be kind of cool if we took an opportunity to see something actually from the moon. So what I have with me today from our friends at NASA, I brought actual moon rocks.
Whoa. Whoa.
And you guys are going to get a chance to look at these up close today. You guys ready?
Yeah.
Let's do it. You guys got an opportunity to make craters on the surface of the moon and see what we can learn by actually looking at the moon. And then you guys got an opportunity to actually hold some moon rocks. Was that pretty cool?
Yeah.
You guys did greater than I ever thought you would. Nice work. We're now joined by Pris Strain, the curator for the moon rocks we have on display here in the museum. Thank you so much for talking with us today.
Oh, I'm happy to be here.
And we're standing here in front of images of the Apollo landing sites where the astronauts actually were able to pick up the rocks and bring them back. Can you tell us about the rocks that we have on display here?
Oh, yes. We have a rock from Apollo 15 that was collected by astronaut Dave Scott, and it's 3.3 billion years old. Then we also have an ancient rock from the lunar highlands, and it's 4.36 billion years old. Moon rocks are really old. We also have 2 samples from Apollo 17, which were collected by the astronauts Jack Schmitt and Gene Cernan. We have a rock, and we also have a sample of lunar soil.
Outstanding. So visitors to the museum can actually come here and see those.
That's right.
All right, now guys, on the video that we watched, those students got a chance to actually hold moon rocks. That was pretty cool, wasn't it?
Yes.
All right, well, I've got a surprise for you. Officer, could you come here, please? Thank you. All right, let's see what's in this case here. So what I've brought in are actual moon rocks that you guys are going to get a chance to look at. Now, what I think is really cool about this lunar sample disk is that this disk holds samples from 4 different manned missions to the moon, Apollos 14, 15, 16, and 17. So in this disk, it represents 4 times that man went to the moon. And I'm going to give you guys a chance to actually look at these. So I'm going to hand that to you, and you guys can take the magnifying glasses and check that out. Now, Pris, you were telling me earlier that this sample actually tells the story of the moon. How is that?
Oh, well, the lunar rocks are very, very old. So it's a way of looking back through time and learning about the earliest history of the moon.
And the first one that we're going to talk about is anorthosite. What does that tell us?
That's right. An anorthosite is a light-colored rock that's made up almost entirely of just one mineral, which has a kind of funny name. It's called plagioclase feldspar, and that's a common rock-forming mineral on the Earth. And the anorthosites are found very much in the ancient lunar highlands. And so that tells us about the development of the early lunar crust.
Okay, and then and actually it's light colored, so when we go out and look up at the moon at night and we see that it's got light areas and dark areas, those light areas, we're actually seeing anorthosite, just like these guys are holding right now.
That's right.
That's really cool. Now, there's also a couple other kinds of rocks in there that help tell that story.
Another rock we have is called a breccia, and that's an Italian word, and it means a rock that's made up of irregularly shaped fragments of other rocks. And on the moon, breccias are just smashed up, beat up rocks that were little pieces of other rocks are all smashed together. And that tells us about the violent early history of the moon when it was bombarded by meteors and asteroids and maybe comets. And you see all the craters on the moon, you can see that was a very heavy bombardment of the surface, and we can read that in the rock.
Very violent, it sounds like. Mm-hmm. And how about the third one?
The third one is called a basalt, and that's a dark-colored igneous rock, and igneous means that it formed from melted material that cooled and hardened, and the basalts form the very flat lowland plains on the moon. And an interesting thing about lunar basalts is that lunar basalts have more titanium than Earth basalts.
Oh, wow. Now, teachers, if you think this is pretty cool, you can actually become Lunar Rock certified to check out this lunar sample disc, and NASA will send it to you, and the best part is it's free to use in your classroom. Now, visitors that come to the museum have an opportunity to do something that I think is incredibly cool. They can actually touch a moon rock. Tell us about that.
Yes, the touch rock that we have at the museum was collected on Apollo 17, and it's a basalt, and when you look at it, maybe it looks kind of plain to you, but when you think about it, it's a really amazing rock. It's 3.8 billion years old, and it was exposed on the surface of the moon about 100 million to 125 million years ago, probably by a crater impact, and it sat there waiting until 1972, when astronaut Jack Schmitt, who was the only professional geologist who was an astronaut who went to the moon, he picked it up and brought it back to Earth, and then in 1976 it found a home here in the museum, so you can come and touch a piece of another world.
That's incredibly cool. I know my son loves to come here and actually go over and find the moon rock and touch it. That's so cool that visitors can come touch a piece of another world. Now, when Neil Armstrong took the first steps on the surface of the moon, he was wearing a spacesuit, and that spacesuit is currently in conservation out at the Stephen F. Udvar-Hazy Center, and I had a chance to talk to one of the conservators about how they're dealing with the moon dust still on that suit. Check this out.
I'm joined by Lisa Young, a conservator here at the National Air and Space Museum, and we are in the conservation lab at the Stephen F. Udvar-Hazy Center. In front of us is Neil Armstrong's spacesuit that he wore when he took the first step on the moon. Now, this suit's still covered in moon dust, right?
Yep.
What can you tell us about that moon dust?
The moon dust is mostly on the bottom half of the suit. You can see it where it's discolored to a little bit darker gray. And the moon dust is made of grains of soil or minerals that are very sharp and angular. There's no atmosphere on the moon, so the grains and particles of sand don't get worn down. And they cut into the suit fabrics and have embedded themselves between the fibers of the textile.
And it's not just one type of grain of moon dust, right?
Right. Scientists have identified 6 different types of grains, and you can see them under the microscope pretty clearly. And we can see them here on the surface of the suit.
And so when you're conserving this suit to eventually go back on public display and to keep it for generations to come, you have to think about that moon dust in your work, don't you?
Right. We don't really want to clean off the moon dust. It doesn't come off easily, but there is other types of dust that have gotten onto the suit. So we use special techniques to make sure that the moon dust will remain on the fabric and that we get off unwanted dust from storage and display.
Awesome. Well, thank you so much for talking to us today.
Sure.
Okay, Tom, Pris, we have looked at rockets that got us to the moon. We have looked at new features on the moon. We have looked at moon rocks. Aren't we done studying the moon? Why are we still looking at the moon?
Oh, well, the moon has a very, very special relationship to the Earth, and it's also very special in the solar system because it is our closest neighbor. And this connection goes back to the moon's origin, and from there, it even extends to today, because the Earth and the Moon still affect each other. I mean, we know about the tides, right? The Moon actually influences the rising and falling of the tides on the Earth, the bodies of water, the oceans. That the Earth also has that same effect on the Moon. It's raising solid tides on the Moon. And that kind of flexing that's happening is actually helping to organize these very young faults that I was talking about earlier that indicate that the Moon is shrinking. So the Earth, in a real way, is still helping to shape the Moon today.
And Pris, the moon rocks that we have, people are still studying them. Is that correct?
Oh yes, every year NASA sends out more samples to investigators who request them for specific research projects. And we're still learning things about the rocks and new things about their composition that we didn't know before.
Okay, now you guys ready for a couple more questions?
Sure.
So let's go to an online question. Have we found any new materials that are present on the Moon?
Well, we did find some new minerals on the Moon, and we found that they were minerals that are formed at high pressures. And this comes from all the cratering on the Moon and all the bombardment on the Moon that creates high pressures in the rocks and can help form new minerals. They found a new mineral. It was called armalcolite, which was named after Armstrong, Aldrin, and Collins, the Apollo 11 astronauts, which we hadn't known of before, but later found at an impact crater on the Earth. There was also a mineral called tranquilityite, and one with a really strange name, pyroxferroite.
That's a lot to remember. Okay, we have an audience question. What's your question?
How are craters formed in the Moon?
How are craters formed on the Moon?
Well, as you can see, there are lots of craters on the Moon, and they're formed when meteors or asteroids or even maybe a comet hits the Moon and really hits the surface hard, and then material from underneath the surface gets thrown out. So we can learn about the subsurface of the Moon by studying craters.
Well, I want to thank you two both for being here today. That's all the time we have. I also want to thank the International Titanium Association. And this is our last show of the school season. We'll pick up again in September. We've got some really exciting topics. Let's give you a little look. Thanks so much for watching today. We hope to see you in September. That was really great. I love this exhibit. There we go.